So part one. All right, so I'm going to start really at the bottom. So starting with definition. So artificial intelligence is essentially making computers think like humans. Machine learning is a part of AI. It is a field of AI that allows computers to learn without being explicitly programmed. And deep learning is a subset of machine learning using neural networks and using actually multi-layer neural networks that allow you to solve a whole host of new types of problems that were not easily solvable about 20 years ago. Now, we'll talk about this in a moment, but it turns out, although deep learning is considered a subset of machine learning, the reality is that in some ways you can actually see machine learning as a subset of deep learning, and we'll explain why that is the case. So firstly, why AI? So AI is basically about transforming, the way I see it is about transforming data into information. So somebody gives you some raw data, you essentially are asking questions. And when you're answering a question, you're getting information from that. So an example would be, the raw data would be the heartbeat. And the information is whether or not somebody has a heart problem or not. If you have a picture of Marilyn Monroe, just to know that that's Marilyn Monroe, that would be the information. Historic sales would be your data, and forecasted sales is the information that you're actually getting from that. Same thing is you see a bunch of notes, that's pretty useless unless you, for example, know that this is something that was composed by Mozart and has all kinds of other things around there. So data is good, but information is better. And so it's basically about extracting information from as much as possible. And information is ultimately what we use to make decisions with. And so when you talk about self-driving cars and so on, it's all about extracting information about the road and about road conditions and so on. And based on all that information that's being generated, to make decisions about what set of steps to take. But the raw data is simply the ingesting of road signs and traffic signs and things like that. So the history of neural networks. So the Mark I perceptron machine is old. It goes back to the late 40s, early 50s. So in a sense, this was the first neural network. The grandfather of all neural networks came in around in the early 50s. To some extent, you can argue that Alan Turing himself inspired a lot of the thinking about AI around that time. But it was really the Mark I perceptron machine that kicked it off. For about 20 years, it was an incredibly exciting era. That was around the time that people started to envision computers like HAL 9000 and so on. This was sort of like people began to really believe that we'd have AI today, like an actual general purpose AI. The 1970s, it hit reality. So reality kind of sunk in that people realized that firstly, the algorithms were not there, and secondly, the computing resources weren't there. And so that became known as the first winter of AI. Then the 1980s, once again, things started. So the only thing that happened in the 1970s, and this sort of came from work in the 1960s, was work with expert systems, which are a branch of AI that we will not talk about. But it had some moderate successes in the medical space. So basically making decisions about whether somebody had a disease or not. That was kind of what expert systems did. When we moved to the 1980s, that's when a lot of the critical developments in AI, in modern AI, started to happen with machine learning and deep learning. This was something called a multi-layer perceptron, and in particular, the backpropagation algorithm was developed in the 1980s by a guy by the name of Geoffrey Hinton, who was a professor at the University of Toronto, one of my alma mater. And so during the 1980s, that was kind of, that started to develop. Then we hit the second winter in the 1990s when, again, you ended up seeing limitations of compute power. Also, algorithm reach was fairly limited. Typically when you dealt with multi-layer perceptrons, there was simply one hidden layer, which essentially prevented the AI from essentially developing any really deep insights. So a lot of really complex types of problems like vision and so on simply could not be addressed during this time. It was not something that was feasible. Then coming into the 2000s, that was kind of the modern era of machine learning, which continues until the present. This is where you have multiple layers, not just a single layer, for neural networks. You have fairly sophisticated algorithms. It can roughly be described as roughly 3 different branches, which I'll talk about in a moment. And we're developing new learning methods. One of the things that came out just towards the end of last year by Jeffrey Hinton is a new way for, it's actually approximates brain function a little bit more. We've actually incorporated that into AI Studio as well. So it's kind of, but we'll talk a little bit about that later. But we're seeing a lot of really exciting, very new fields starting to develop out of this. I do think winter is coming. So there's going to be another winter, which will essentially be, we're going to hit some limitations again, largely because one of the challenges that we're going to be looking at is how do you build knowledge representations of the world? And there are 2 problems I would say in machine learning. One is building like a truly effective knowledge representation of the world. And the second thing that's really tough is getting machines to generalize and to extract rules from its observations. Nobody knows how to do that yet. If you can figure it out, then you get a Turing Award. So, okay. So, what is machine learning? Ultimately, it's, so the way to describe it is a computer program is said to learn from an experience E, with respect to some class of tasks T and a performance measure P. If its performance at tasks in T are measured by P, it improves with experience E. So what that basically means is that you essentially give a set of experience, which is training data, to a machine to perform a certain set of tasks, which could be, for example, determining whether somebody has a tumor or not, or whether it's hot dog or no hot dog. And the performance could be measured many different criteria. It could be, for example, how accurate your models are. It could be what sort of loss function, what kind of loss should your model have. It could be things like false positive rates and things like that. So all of these go into these are all possible measures P. So a task T is, as I said, it's a classification problem, whether comment on a form is appropriate or not. Performance could be classification category, accuracy, and experience is the corpus of data that's used to actually train models. So all deep learning problems or all machine learning problems ultimately can be described as that. So it's a set of experiences E that are then used to train to perform some task T measured by some performance P. So one of the other things that so although machine learning is considered a subset of deep learning, deep learning is considered a subset of machine learning, it's actually the other way around. And the reason for that is there's something called the universal function approximator theorem that's actually has been proved. So what the universal function approximator theorem says is that any deep learning or any machine learning problem can be approximated by a deep learning problem. So what that means is, so when you look at what a deep learning system is, it's essentially a set of matrices where you take you multiply a set of matrices and provide a bunch of nonlinear functions on that, and eventually you build something that approximates a function. So the way to think about it is that if you have an input, for example, with a picture of a puppy, and you want the output is the word puppy, the whole point of machine learning is to figure out what that function f is to the closest possible approximation. And anytime you see kind of an input to output statement like that, for example, with any machine learning problem, in effect, you can build a deep learning model that will roughly approximate that. So how close you approximate that function is called the error of that model. So if you are far away, then the error is quite high. If you are close to it, then the error is low. But ultimately, this is this function is essentially what you're trying to derive. There are many different types of names for it. You can call it an inference model. You can call it an estimator. You can call it all kinds of things, but essentially all machine learning problems can be boiled down to this one statement. So machine learning is probabilistic in nature. You cannot make any definite state. You can't really say with any certainty or with absolute certainty whether something is A or B. It's always a probability. So when you build a model, the model will only give you a given result with a certain level of probability. So for example, in this picture, it says the probability that there's a woman in this picture is 61%, 82% that there's a Labrador retriever in this picture, 77% is autumn, 38% this woman is walking, 57% there are trees in this picture. Now, depending upon where you set the threshold, so a threshold is like your kind of an agreed upon statement saying, okay, anything above 50%, for example, I'm going to accept as true. Anything below 50%, I'm not going to accept as true. So in that case, for example, if I set 50% as my threshold, then walking is clearly below that. So you can't actually make a statement that the woman is walking if the threshold is 50%. You can say that there's a woman, you can say there's a Labrador retriever, you can say it's autumn, you can say there are trees, but you can't say that she's walking. But the statement is that you set the threshold as either being like whatever your threshold is. So you can either essentially balance your model towards more false positives or more false negatives depending upon your threshold. So if you set the value very high and say it's 80% is your threshold, then what you're trying to do is bias your model towards bias your results towards fewer. You're saying there are going to be fewer false positives, whereas if you like set it very low, then you're saying, well, there are going to be more false positives. So depending upon what you're trying to get to. So in terms of what AI is good for, there are many different applications of AI. Forecasting and prediction is a very good example of that. For example, in the financial markets, this is an area that we've actually used forecasting quite a bit. We've used it to predict, like what you could, in theory, use it to predict heart rates as well down the line if you want to do it sort of a time series analysis of somebody's heart rate. You can do things like predicting CPU behavior. You can predict thermal properties of a data center. All these could be part of forecasting. Anomaly detection is where the system learns what a nominal state of the system looks like, and then determines anything that's out of whack with that, what the nominal state is. An example of that would be to train an AI on what the normal network behavior is in a network. So what the normal traffic patterns are. And so that an anomaly could be that there's an intrusion event detected. So that would be because your traffic patterns in your networks have changed. Object detection is pretty clear. Picture of a dog, so with a bounding box around it. That would be an example of object detection, and to be able to determine what exactly is it that you're looking at. That's pretty clear. Pattern detection is a little bit different. Pattern detection is where you start to notice, where you can start to form clusters. An example could be that how your customers are segmented. It could be that that things can be grouped in certain ways that may indicate some underlying connectedness between them. For example, customer segmentation is obviously one. Another example could be, which I was just talking to with a hospital in Europe about different states that a human can occupy. So, for example, different patients would tend to cluster in different ways, depending upon how they reacted to some drug. So a lot of these things, and AI can actually determine what those patterns are. Auto generation is something that is relatively new. There are several ways in which this can happen. So, for example, autoencoders are one way to do this. Another thing are GANs. So GANs are a research area that's just started developing. So AI Studio, we recently worked with GANs to predict new types of materials. You can use it for example, drug discovery could be one thing, generating simulation data, running simulations of a system, for example, learning patterns in how a market behaves. You can then generate training data or simulation data based on previous patterns. And then enhancement or reconstruction. So for example, this could be upsampling, and it could be essentially telling a system that how do you go from like a 2K image to a 4K image? So an AI can actually determine those gaps and actually construct a higher, like a more higher resolution image based on that. It can also, from partial information, construct a more complete picture. So, you know, in some of these detective shows, they just get a picture of somebody's face, and from that they reconstruct the whole thing. I don't know whether that's possible necessarily, but it's certainly one thing that you can actually use it from partial data to assemble a complete data set. There are many other applications of machine learning and AI, but it's just one segment.